Hi everyone, my name's Adam. In this problem, what we're going to be doing is filling out the table for a savings account where interest is being compounded continuously. And what we have to start with is an initial investment amount of $1,000, an annual interest rate of 12%. And what we want to find is the time to double, or namely the time to double our initial investment, and the amount that will be in the account after 10 years. So to get started, let's review just a little bit. So we've been talking about differential equations and exponential growth and decay, but we've seen maybe in previous courses things about compound interest. So you may recall a compound interest formula looks something like this. A, which is a future amount, is equal to some initial amount, or principal P, times the quantity 1 plus R over N, where R is our annual interest rate. N is, say, the number of periods per year that we're compounding, and this is all raised to the n times t power, where t is usually time in years. Okay, so this is if you're compounding only a certain number of times per year, say quarterly, 4 times per year, monthly, 12 times per year, but we're compounding continuously. Compounding continuously, and we had a formula for that. So A, future amount, is equal to P, the principal, times E to the R times T. So this is what we're going to work with, or at least build on for right now. So to get started, if you have seen this formula before and you're familiar with it, you could actually just use this to answer or fill out the questions in the table. But we're going to liken this to our exponential growth and decay model, which looks like y is equal to c times e to the kt. So if we look at this and we look at our continuous compounding formula, they look pretty similar in that y is going to be our future amount where so far we've used this to find the future amount that's going to be, say, in a population after time t, but now we're talking about money in an account after time t. C, which is our initial value, that's our initial amount starting in our account, which we know, say, is $1,000. K, which so far has typically been some rate of growth of our money for right now, is our interest rate. So this is the interest rate, which is 12%, or as a decimal, 0.12. And T is going to be time in years. Okay? So using this, we'll go ahead and get started. So I think it's easiest to start with the last part, or simplest part first, finding the amount that's going to be in the account after 10 years. And so that's simply taking t equal to 10, the future amount y is equal to 1,000 times e to the 0.12 times the value of t, 10. So all we have to do is evaluate the right-hand side. So 1,000 times e raised to the 0.12 times 10 power gives us approximately 3,320.12. And we'll go ahead and start filling out our table. So the amount after 10 years, now this is an amount in dollars, is going to be $3,320.12. So that's the first part. The last part is the time to double. So what do we want here? Well, time to double is the value t, or time, to double, say, our initial amount, c, which is 1,000. Okay, so to get started, we're going to fill in the right-hand side of our equation, right, or exponential growth equation here, So this is going to be equal to 1,000 times e to the 0.12t. So what we're trying to do is find the value of t such that our initial amount is doubled. Well, what's double of 1,000? 2,000. So we're trying to solve the equation 2,000 equals 1,000 times e to the 0.12t. So we've done things like this before in algebra. So what we want to do is first isolate the term with the variable on one side. So we'll divide through both sides by 1,000. So that's going to give us the equation 2 is equal to e to the 0.12t. Now again, we want to solve for the variable t, and t is in the exponent position. So again, from algebra, a way to bring the exponent, a variable, out of the exponent down in front is to take the natural log of both sides. So we'll take the natural log of the left, so the natural log of 2, and the natural log of the right. So this will give us the natural log of 2 is equal to just the exponent 0.12t from our previous step. And of course, we just want to solve for t, so we'll divide both sides by 0.12. So this gives us t is equal to, say, the natural log of 2 divided by 0.12, which gives us say approximately 5.78. And filling the last part of our table, the time to double is 5.78, but that's the value of t in years. Thank you very much.